Good morning, Mananda. Myself, Sreevani, working as an assistant professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal, Hyderabad. So, in the today's lecture, we are going to learn about uh, the problems which are associated in the module 4, that is transmission line characteristics in electromagnetic waves and transmission lines. Right? So, in this particular one, we will be discussing about the question bank, which is consisting of long answer, short answer, and analytical type questions. So first we are going to learn about short answer type questions, which are in the transmission line characteristics. So first, define transmission line. So transmission line is a conducting system, two-way conducting system in which the electrical energy or the power is to be transferred from one place to the another place. That is from source to the destination. There must be some physical connection which is to be associated with the one node to the another node. Right? So transmission line is a two-way conducting system in which electrical energy or signals need to be transferred from source to the destination or one point to the another point. Then draw the equivalent circuit of a transmission line. So basically it consisting of four primary constants of a transmission line. Those are resistance R, inductance L, and the capacitance C, and the conductance G. So the equivalent circuit of a when transmission line means there are two series elements which are connected in the circuit are represented with R and inductance as L, and the two parameters which are connected in the shunt or parallel connection is represented with one is with the capacitance and another one is with the conductance G. So the shunt elements which are connected in the series manner as resistance R and the inductance L, and the two capacitance C and the conductance G are connected in shunt, and this is the equivalent circuit for the transmission line. Basically, it consisting of four primary constants of a transmission line. Those are resistance or inductance L, conductance C, G, and the capacitance C. Right? So the current flowing through that input terminals are given by II, and the output terminals are given by here I naught, and at the load means at the output side will be connecting the load resistance RL. Now through that the load current IL is to be considered. This is the equivalent circuit of a transmission line. Then write the differential form of the transmission line equations. So consider this is the simple circuit diagram for the transmission line equivalent circuit. From this we are going to write the differential form of the equations as to be dV by dx is equal to minus of R plus j omega L into I, and di by dx is equal to minus of g plus j omega c into v. Right? These are the two differential form of transmission line equations. Right? dV by dx is equal to. So to write these two equations, we just consider which are the elements connected in the series case as resistance R and inductance L, and for the shunt case capacitance C and the conductance G need to be considered. Now from that dV by dx is equal to minus of R plus j omega L into I, and di by dx is equal to minus of g plus j omega C into V. Right? So these are all the differential form of equations for the transmission line. Then describe the different types of distortions in a transmission line and condition for distortionless transmission line. So different types of transmission lines distortions means there are two cases we have considered in this particular transmission lines. One is phase distortion, and another one is this phase distortion is also called as delay distortion, and one more is frequency distortion. There are two types of distortions we have considered in the case of transmission lines. One is phase distortion, it is also called as delay distortion, and another one is frequency distortion. And the condition for distortionless transmission line means L by C equal to R by G. Right? So the inductance and the capacitance, resistance R and the conductance G or 4 are called primary constants of a transmission lines. Next, define intrinsic impedance or characteristic impedance of free space medium. So, intrinsic impedance or characteristic impedance is represented with Z0 in the transmission lines, and it is expressed in terms of all the primary constants, means R plus j omega L by G plus j omega C root over. Means it is given by, it is the ratio of the input voltage to the input current, or in terms of intrinsic impedances means it is related to the fields, and it is given by electric field strength to the magnetic field strength. Now for the characteristic impedance means we used to represent it with Z0, then that is given by root over R plus j omega L by G plus j omega C, where it includes all the primary constants of a transmission line and along with the operating frequency as omega. Next, define wavelength and phase velocity. Wavelength is represented with lambda, that is given by 2 pi by beta. How we'll define this wavelength means after every 2 pi radians, the phase changes are going to take place, and it is represented with wavelength as lambda, which is equal to 2 pi by beta. And the phase velocity, or it is also called as wave velocity, it is represented with Vp, and it is given by the ratio of angular frequency to the phase constant as omega by beta. For a free space medium, its value is 3 into 10 power 8 meters per second, and it is represented with V0. In the transmission lines, we used to consider it as Vp equal to omega by beta, that equal to 1 by root over mu epsilon. The waves case, right? Wavelength means after every 2 pi radians, the phase changes are going to consider as takes place. Hence, it is represented with lambda. The formula is given by lambda equal to 2 pi by beta, and the phase velocity, it is also called as wave velocity. It is represented with Vp equal to omega by beta. Now, some more short answer questions are defined as here group velocity. So now to define group velocity, we need to consider envelope of frequency components and the phase constants, that is represented with Vg. So V is the notation for velocity, G stands for group. So group velocity Vg is given by d omega or dou omega by dou beta, which is equal to omega 2 minus omega 1 by beta 2 minus beta 1. This is the equation called group velocity. Then, describe the condition for loading in a transmission line. So, along with the two parallel wires of a transmission line, we just add one more extra shunt line to the parallel wires of a transmission line, and the patches or for a lumper section line, we are going to add one extra line inductance which is connected in a series of the two parallel wire lines, and it is said to be loading. Next, write secondary constants in terms of primary constants. As we know that all the primary constants means R, L, G, C, and secondary constants means these are all primary constants, and coming to the secondary constants, these are given by secondary constant Z0 and gamma. Characteristic impedance of a transmission line is represented with Z0, and the propagation constant is represented with gamma, and these two are called secondary constants of a transmission lines. And the primary are all represented with R, L, G, C. Now we want to write the secondary constants in terms of primary constants. Means, as we know that characteristic impedance Z0 is equal to formula as R plus j omega L by G plus j omega C, and propagation constant gamma equal to root over R plus j omega L into G plus j omega C. Right? So if you multiply these two, Z0 into gamma equal to R plus j omega L by G plus j omega C into root over into R plus j omega L into G plus j omega C root over. So this gets cancelled. Then Z0 into gamma equal to R plus j omega L. Similarly, if you divide these two, Z0 by gamma, then you're going to get Z0 is r plus j omega L by g plus j omega c by, and in the denominator, if you're going to write the propagation constant as r plus j omega L into g plus j omega c, then these two terms gets considered as here z naught by gamma equal to r plus j omega L by g plus j omega c by root over r plus j omega L by into g plus j omega c, right? So in this case, g plus j omega c and g plus j omega c, r plus j omega L, r plus j omega c gets cancelled. Then this becomes 1 by g plus j omega c is left out. Suppose if you consider the reverse ratio as gamma by z naught, then it becomes g plus j omega c. This is the way we can write all the secondary constants in terms of primary constants of a transmission lines. So all the primary constants of a transmission lines are represented with RLGC, and secondary constants are z naught and gamma, characteristic impedance and propagation constant. Next, calculate the characteristic impedance of a quarter wave transformer if a 120 ohm load is to be matched to a 75 ohm line. So to find this, generally the formula is given by Zn is equal to Z0 square by ZL. Input impedance of a transmission line which is terminated with a quarter wave transformer, then it is given by Zn is equal to Z0 square by ZL. So to calculate the characteristic impedance of a transmission line, then we need to consider Z0 square is equal to Zin into ZL, which is equal to Zin value as this one 75 ohms and the load is given as 120, then Z0 is equal to root over 75 into 120 becomes the characteristic impedance of a transmission line. For a quarter wave transformer, the input impedance of a transmission line is given by Z0 square by ZL. Now from this, Z0 need to be calculated. Then write the solution for P and I in exponential form. As the transmission line V and I equations are to be expressed as V plus into e power j omega t minus gamma L plus V minus e power j omega t plus gamma L, and I equation is to be I plus e power j omega t plus gamma L minus I minus into e power j omega t plus gamma L. Basically, it consisting of two traveling waves. One is e power j omega t minus gamma L is to be in forward direction, and e power j omega t plus gamma L represents it will be moving in backward direction. And the V plus and V minus are the magnitudes of the forward traveling wave and backward traveling wave. And similarly for I components also, I plus and I minus are the two magnitudes of the current wave equation, which is to be expressed in terms of exponential form of the transmission line equations. Then what are the different types of transmission lines? Depending upon the frequency ranges, if you want to transmit, then we have different types of transmission lines. One is parallel wire type, also called as open wire type, and the second one is like coaxial cables, and the third one is the type of waveguides, and fourth one is the type of optical fibers. Now to transmit high frequency signals means the range will be up to gigahertz, means then we used to consider here a type of this one is optical fiber cables, right? So there are four different types of transmission lines we have considered in the case of transmission lines: parallel wire type, also called as open wire line type, and coaxial cables and waveguides, and optical fiber type. So now to send high frequency signals, we used to consider the fourth type of one is called optical fibers, right? So group velocity can be defined as it is the ratio of the change in the angular frequency to the change in the phase constant. And to consider the condition for loading of a transmission line, we just add one extra series line in parallel to the parallel wires. And the secondary constants in terms of primary constants means Z0 into gamma equal to R plus j omega L. Similarly, Z0 by gamma equal to 1 by j omega C. Now gamma by Z0 equal to g plus j omega C. Now to calculate the characteristic impedance of a quarter wave transformer, we used to consider Zn is equal to Z0 square by ZL. And for now to express voltage and current equations in the exponential form, then V equal to V plus e power j omega t minus gamma L plus V minus e power j omega t plus gamma L. And I equal to I plus e power j omega t plus gamma L minus I minus e power j omega t plus gamma L. And we have discussed four types of four types of transmission lines as parallel wires, coaxial cables, waveguides, and optical fibers. Now, in order to write the long answer type questions, we used to express all in elaborately. First, what is meant by a circuit or a definition related to that. Then followed by is there any derivation part related to that. We need to write neatly the mathematical equations. And finally, we should express each and every term which is associated in that particular derivation. So here, starting from the equivalent circuit, derive the transmission line equations for V and I in terms of source parameters. So in order to write the equations here, first we need to draw lumped element circuit, equivalent circuit of a transmission line, which includes all the primary constants of a transmission lines as R, L, G, C. And then followed by we need to write apply KVL or KCL equations to write simple equations. Then we should consider differential components of both the voltages and current equations. dV by dx is equal to minus of R plus j omega L into I, and di by dx is equal to minus of G plus j omega C into V. Then if you are again differentiate, then you're going to get second order differential equations. Now from that, if you find the solution for that second order differential equations of a transmission line, then we will be getting the value as for the equations as V equal to V plus e power j omega t minus gamma L plus V minus e power j omega t plus gamma L. And I equation is to be obtained as I plus e power j omega t minus gamma L plus minus I minus e power j omega t plus gamma L. Right? So first we should draw lumped element circuit for a small section of a transmission line equivalent circuit. In that, it consisting of only all the primary constants. The two elements are connected in series. Those two are resistor R and the inductance L. And the shunt elements which are connected in that are capacitance C and the conductance G. Based upon that, we will apply loop equations. Now from that, we are going to consider differential components of voltages and currents equations. Now again, if we substitute I and V by the node voltages according to that, then we'll be getting second order differential equations as the transmission line equations. From that, the solution need to be considered as for second order differential equation for voltages and currents. These two are the relations. Then from the fundamental voltage and current equations of transmission line, derive the expression for input impedance of the line. So from this, if you are going to write the equation for Zin, means V in by IM. Input voltage to the input impedance of a transmission line can be defined as it is the ratio of the input voltage to the input current. So in order to define this one, we just consider magnitude terms of either forward traveling waves or backward traveling waves. And after simplification, we are supposed to get the equation as in terms of for a lossy transmission line or for a lossless transmission line. First, if you have to express that one in terms of lossy transmission line, then it is given by Z0 into ZL plus JZ0 tan beta L by Z0 plus JZL tan beta L. This is for the lossless transmission line. For a lossless transmission line, we just assume attenuation constant alpha equal to 0, hence it consisting of only phase constant, that is beta only. If it is lossy means we just consider along with the attenuation constant and we have to replace beta by gamma over there. Why? Because gamma equal to is constitute the attenuation constant alpha and the phase constant beta. Now, describe the different distortions on a line and derive the condition for distortionless transmission line. So different distortions in a transmission line means we have to assume it as two cases of distortions we have to consider: delay distortion or phase distortion, and the second one is frequency distortion. So different frequency means at the load and the source case, the frequency components are deferred case, then it is said to be frequency distortion, and the phase components are deferred in the case of source as well as the load, then that type of distortion is said to be phase distortion, and sometimes it is also called as delay distortion. Now, for a condition for distortionless transmission line case, we just assume their resistance R is equal to conductance G equal to 0 in that particular. Then from that, we'll be getting the attenuation constant alpha and the phase constant beta, along with that characteristic impedance Z0 also. Okay. Then next one is derive the characteristic impedance Z0 from the initial equation of a transmission line. So to derive this characteristic impedance of a transmission line Z0, we should write the equation for this Z0 in terms of all the primary constants of a transmission line. So this can be considered as the root over R plus j omega L by G plus j omega C. So it includes all the primary constants of a transmission line as R, L, G, C, and along with the operating frequency of a transmission line, that is includes omega. Next, derive the propagation constant from the general equations of the voltage and current. So to get the propagation equation, again we have to consider transmission line equations, either voltage or currents. Now from that, the propagation constant gamma can be written as gamma equal to attenuation constant alpha and the phase constant beta, which is equal to, it should be expressed in terms of all the primary constants and the operating frequency. Then it is given by R plus j omega L into G plus j omega C. Right? All the primary constants means R, L, G, C, and operating frequency is represented with omega. Right? So for a characteristic impedance and the propagation constant gamma are said to be secondary constants of a transmission line, and all the primary constants of a transmission line means R, L, G, C are the primary. Now derive the expressions for in terms of primary. Derive the expressions for Z0 and gamma means propagation constant and characteristic impedance in terms of all the primary constants. As we have seen in the that case, if Z0 is equal to this one and propagation constant gamma equal to this, then we should write, if we multiply Z0 into gamma, then it becomes R plus j omega L by G plus j omega C is the formula for the Z0 into root over R plus j omega L into G plus j omega C. Now, multiplication case, these two gets cancelled. Z0 into gamma equal to R plus j omega L is the formula. Now, division case, Z0 by gamma or gamma by Z0 equal to root over R plus j omega L by G plus j omega C into 1 by root over R plus j omega L into G plus j omega C. And this gets cancelled. We have to left out here G plus j omega C only. Now if you consider gamma by Z0, it should be G plus j omega C. This is the way we have to express all the primary constants and secondary constants in terms of one and another. Now define wavelength, velocity of propagation and group velocity and write the respective equations. Wavelength lambda is to be represented with lambda. Lambda equal to 2 pi by beta. Suppose if you consider one wave as a characteristic wave will be moving in this direction, if the phase is going to change after every 2 pi radians. Right? So from this is the one which is considered to be as lambda. Now from this we will define lambda can be equal to 2 pi by beta. Beta be the phase constant. So wavelength means it is the every 2 pi radians the phase constants are going to change, and the wavelength is to be considered as lambda equal to 2 pi by beta. The velocity of the propagation, it is said to be wave velocity or phase velocity, and it is given by omega by beta. This is the ratio of the angular frequency to the phase constant as beta. Now coming to the group velocity, it is represented with Vg and it is given by dou omega by dou beta, and which is equal to omega 2 minus omega 1 by beta 2 minus beta 1. Change in angular frequency to the change in phase constants represents or gives us group velocity. Next, define a transmission line and explain the primary constants. So, transmission line is a two-way conducting system in which electrical signals or energy are to be transferred from one region to the another region, or one point to the another point, or source to the destination. So, now to define it, transmission line, there must be physical connection is to be established between two nodes, and explain the primary constants. So there are four primary constants of a transmission line. Four primary constants of a transmission line. Those are R, L, G, C. Throughout the length of the transmission line, the resistance is uniformly distributed. Throughout the length of the transmission line, inductance L need to be uniformly distributed. And throughout the length of the transmission line, conductance G need to be distributed. And C also need to be distributed. So depending upon this, there are two different types of parameters we have to consider. One is lumped parameter section, as well as another one is distributed parameter section. Lumped parameters and distributed parameters. So all the primary constants of a transmission lines means R, L, G, C are said to be primary constants of a transmission line. Next, what is characteristic impedance? Obtain the relation between characteristic impedance on the propagation constant. It is the ratio of the characteristic impedance is given by, it is the ratio of the input voltage to the input current, and it is to be expressed in terms of, means as we know that Z0 is equal to root over R plus j omega L by G plus j omega C, and propagation constant gamma equal to root over R plus j omega L into G plus j omega C. Okay. Next, explain different types of transmission line parameters. As we know that depending upon the length of the section, we have considered two different types of the parameters related to the transmission lines. We have learnt in the case of transmission line characteristics, that is, first one is lumped section, lumped element section, and the second one is distributed element section. So for the lumped element section case, we'll have four primary constants which are connected in the circuit. That is, resistance or inductance L and the capacitance conductance 2 need to be connected in shunt manner. This is the a simple equivalent circuit or lumped equivalent circuit of a transmission line. R, L, G and the C need to be connected in that particular one. That means if the total transmission line is divided into each small sections, that is, each and every small section is said to be lumped element section. If you consider length will be more in that particular, the collection of all the lumped elements are distributed throughout the length, then the type of parameters are said to be distributed parameters. Right? So there are two types of parameters we have considered in the case of transmission lines as the parameters: lumped element section and distributed element section. Lumped parameters or small section parameters and distributed parameters. Now coming to the analytical. So an airline has a characteristic impedance of 70 ohms and the phase constant of 3 radian per meter at 100 megahertz, means characteristic impedance Z0 is given as 70 ohms and the phase constant beta can be given as 3 radian per meter, and at a frequency of is equal to 100 megahertz need to be considered. Right? So to find the calculate the value of RCL, first we need to write Z0 formula as root over R plus j omega L by G plus j omega C. Right? So in that we just we want to consider here RCL. Three are unknown parameters. To find here along with the omega, we use here the given frequency as omega equal to 2 pi f. Substitute f by 100 megahertz 2 pi into 100 into 10 power 6. So from this you're going to get the omega value need to be measured in terms of radian per second. Now from this if you substitute all the values z0 and beta value, that is beta equal to omega root over LC for a lossless one. So we can consider any of these two formulas to solve all the primary constants of a transmission lines. Next, a transmission line operating at 500 megahertz means f value is given as 500 megahertz. Nothing but 500 into 10 power 6 hertz. Then Z0 characteristic impedance is given as 80 ohms. And the attenuation constant alpha is expressed as 0.04 Nepper per meter. And beta, phase constant beta equal to 1.5 radian per meter is given. Now find the line parameters R, L, G, C. As we know that Z0 is equal to, and from that gamma can be written as, why? Because the attenuation constant alpha and the phase constant beta are to be given. Now from this, see, gamma equal to root over R plus j omega L by means attenuation constant alpha plus phase constant beta equal to alpha value as 0.04 plus j into beta value 1.5 radian per meter is given. From this, we'll be getting the value as gamma. Means attenuation, if you consider the real term, then its value becomes alpha. If you consider the imaginary, value becomes for beta. Now, Z0 value to be expressed as Z0 equal to R plus j omega L by G plus j omega C. Then gamma equal to root over R plus j omega L into G plus j omega C. So by multiplying these two, Z0 into gamma, supposed to get R plus j omega L. And by dividing these two, Z0 by gamma, we're going to get G plus j omega C. Or if you multiply gamma by Z0, which is equal to then G plus j omega C. So by multiplication factor or gamma by Z0 or Z0 by gamma, and along with the Z0 and gamma values, now using angular frequency value as f equal to 500 megahertz means omega need to be considered as 2 pi f. Then in place of f, if you substitute 500 megahertz, that is 2 pi into 500 into 10 power 6 means should be 10 power 9 pi omega value is to be obtained. So we should substitute all the values in that, then we will express all the primary constants equations as R, L, G, C. Resistance R need to be expressed in terms of ohms per meter, and inductance is Henry per meter, and conductance G is mhos per meter, and capacitance C is to be expressed in terms of farad per meter. Why? Because all the parameters of a primary constants are distributed throughout the length of the transmission lines. Hence, all should be expressed in terms of per meter like that. Next, a telephone line has R equal to 30 ohm per kilometer, L is equal to 100 millihenry per kilometer, and G equal to 0, and C equal to 20 microfarad per kilometer. At f equal to 1 kilohertz, obtain Z0, gamma, and phase velocity. Okay. So first RLGC values or previous two problems will have Z0 characteristic impedance Z0 and propagation constant gammas are given. Now we have to express all in terms of primary constants. Now the primary constants are given. We should express all primary in terms of secondary. So as we know that Z0 is equal to root over R plus j omega L by G plus j omega C, which is equal to R value is given as 30 ohm plus J into 2 pi F. F value is given as 1 kilohertz means 10 cube. L value is given as, that is 100 milli, 100 into 10 power minus 3 by G plus means G value is 0 plus J into 2 pi into 1 kilo, that is 10 cube into C value is given as 20 microfarads. 20 into 10 power minus 6 farads. So root over. So to find this, first we have to separate the real and imaginary. Means we should express this one in terms of polar forms as r1 at an angle of theta 1 in the numerator. In the denominator also r2 at an angle of theta 2, then square root of. So root of r1 by r2 we are supposed to evaluate. This value need to be obtained as r. And from this, root of theta 1 by theta 2 means root of theta 1 minus theta 2 to be considered, and root theta formula becomes, that is, theta by 2. So finally, z0 in terms of expressed as r at an angle of theta, or suppose if you want to express this z0 in terms of complex form, that is real and imaginary form, again we have to convert this r and theta polar form into rectangle form. Then z0 can be expressed as some real term plus imaginary term. Then similarly, gamma can be expressed as gamma equal to root over r plus j omega L into g plus j omega c. Same RLGC values are to be substituted. Then gamma can be expressed as alpha plus j beta, where alpha be the real term and beta be the imaginary term. Nothing but phase constant. So to express this one also, we have to first find out the multiplication factor, then separate the real and imaginary terms. Then we have to find this one. First we have to express this one polar form as r at an angle of theta. Then after that we have to express this in terms of real and imaginary by converting into polar form into rectangle form. Okay. So always this propagation constant gamma and the characteristic impedance Z0 must be a complex in nature. And after that, phase velocity. To find phase velocity or wave velocity, omega Vp equal to omega by beta, where omega means 2 pi f by beta, and 2 pi f value is given as 1 kilohertz 10 cube by beta. So from this propagation constant, we'll be getting the phase constant as beta, and this beta value need to be substituted over here then to get the value of this wave velocity or phase velocity. It is represented with Vp. Next, a generator of 1 volt, 1 kilohertz supplies power to a 100 kilometer long line terminated in Z0 and having the following constants: R equal to 10.4 per kilometer, L equal to 0.00367 Henry per kilometer, and G equal to 0.8 into 10 power minus 6 mhos per kilometer, and the capacitance C equal to 0.00835 into 10 power minus 6 farad per kilometer. Then calculate Z0, attenuation constant alpha, phase constant beta, and the wavelength lambda and velocity v. So as we know that how we have evaluated in the previous problem, similarly here also Z0 can be written as root over r plus j omega L by g plus j omega c is the one formula. And in this we just substitute r all values, and omega by your frequency is also RLGC values are given. Now to find here frequency is also given, that is 1 kilohertz. Now from that find the value of omega, that is 2 pi f, nothing but 2 pi into 10 cube. Okay. So this is the value of omega. Then we need to substitute omega by over here. Now to find this again, whatever the procedure we have followed, means to first convert this one into polar forms as r1 at an angle of theta 1 by in the denominator r2 at an angle of theta 2 root over terms. Then to get the values of r and theta, we need to find r1 by r2 one time becomes r, and root over theta 1 minus theta 2 becomes root theta, means the formula becomes theta by 2. Then from that we are getting value as root r at an angle of theta. Now to express this one, again we have to convert the polar form into rectangular form. Then gamma. So to find gamma, we use the formula as root over r plus j omega L into g plus j omega c. First, whatever the values are given for all the primary constants as R, L, G, C, and along with the angular frequency omega, we have to substitute. Then we can separate the real and imaginaries. Then from this, you're supposed to get alpha as the real term, plus imaginary term as the beta. So from this, attenuation constant alpha needs to be obtained and the phase constant beta is to be obtained. Now from that, wavelength is supposed to. So a wavelength lambda can be given by here 2 pi by beta. So whatever the value which we have got it from the phase constant beta, and this beta need to be substituted over here to get the value of wavelength. And the velocity, wave velocity Vp equal to omega by beta. So to find this omega, we use 2 pi into 10 cube by as the value as omega, and beta needs to be from phase constant. And this beta value need to be obtained from the propagation constant gamma, which constitute attenuation constant alpha and the phase constant as beta. Next, a certain transmission line 2 meter long operating at omega equal to 10 power 6 radian per second has alpha equal to 8 dB per meter and beta equal to 1 radian per meter, Z0 equal to 60 plus J40 ohms. And if the line is terminated by a load of, means ZL value is given as 20 plus J50 ohms, then determine the input impedance. Okay. So to find the input impedance of this one, the formula we used to consider as here certain transmission line 2 meter long, means L value is also given as 2 meters. Right? So ZL is equal to, input impedance Zn is equal to Z0 into ZL plus JZ0 tan beta L by Z0 plus JZL tan beta L. So in this, you just substitute here every value, or for a lossy line, it will become as Z0 into ZL plus Z0 tan H gamma L by Z0 plus ZL tan H gamma L. Why? Because why we have considered here gamma means alpha and beta values need to be, alpha and beta are to be given. So alpha and beta exist means gamma must be exist. So alpha plus J beta is supposed to use for the gamma expression. So here alpha is exist means the line is said to be lossy line. Why? Because alpha is the notation for attenuation constant. The attenuation exists in the line means there must be some loss in the signal. Hence the line is said to be lossy transmission line. So here if we are assuming attenuation constant alpha equal to 0, then beta only exists. Hence this is the line for lossless transmission line. Okay. For lossy means we have to consider this as the formula. Now Z0 value is given as 60 plus J40 and ZL as 20 plus J50 and tan H gamma L. Gamma means we have to write 8 plus J 1 radian per 1. This gamma equal to 8 dB plus J. Value is for gamma and L need to be considered as 2 meters. So we need to multiply these two. Then gamma L is equal to 8 plus J into 2. So everything we have to substitute over here then to get the value input impedance of a transmission line. So generally this input impedance is measured in ohms. Okay. Next, lossless transmission line with Z0 equal to 50 ohm is 30 meter long and operates at 2 megahertz. The line is terminated with a load means 60 plus J40 ohms and the velocity U equal to 0.6 c. Then the line, find the reflection coefficient, standing wave ratio and input impedance. First we need to find reflection coefficient. That is the formula is given by gamma equal to ZL minus Z0 by ZL plus Z0. Now ZL value is given as 60 plus J40 and Z0 is given as 50. So using that we can find the value of gamma, and finally we should express this gamma in terms of magnitude and the phase function, where this magnitude need to be considered and the range will be given to the 0 to 1 only. That magnitude we have to consider over here for the gamma. Next is standing wave ratio. Now to find the standing wave ratio is, the formula is S is equal to 1 plus modulus of gamma by 1 minus modulus of gamma. Whatever the magnitude which we have got it from the reflection coefficient gamma, that value we have to consider, and S is to be obtained, then that S value need to be in the range of 1 to infinity. Now after that, to find input impedance, and here see a lossless transmission line. That's why input impedance equation is given by Z0 into ZL plus JZ0 and beta L. Input impedance equation is given by Zn equal to Z0 into ZL plus JZ0 tan beta L by Z0 plus JZL tan beta L. Right? So to find the value of beta into L. So the formula is given by here 2 pi by lambda into L value is 30 centimeters. Okay, this is the way we can consider the value as beta L and substituted over here to get the value of input impedance. So what we have discussed in this particular lecture is some short answer questions and long answer questions, and followed by some analytical questions which are covered in the transmission line characteristics. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.